continue with our journey in Boltzmann universe. I want to start with a remark. After the last course, one of you came to me and remarked that, Hocam, you are really showing your ear like this. He didn't say to me that, I just, and actually you are mixing cause with effect. He didn't say that, but that's what I really was doing. In any case, long story short, he told me that you can deduce the log p from the fact that if you want things to add up when you multiply them, okay, like there is an event of probability PA, there is an event of probability PB, and the two events happening together is PA times PB, and if you want them to add up when you multiply them, then you should go with log. Alper told me that.
But they should be independent.
Yes, they should be independent. Yeah. So you can arrive at log p from there as well, and that's even a better way of arriving at it, even more pure. And then you can use it as the starting point and prove that you get maximum entropy when you have equal probabilities. Does it make sense? You remember, because we said if you want to get maximum entropy when you have equal probabilities, you should have this function as the entropy. You can also say that for the sake of multiplicativity to become additivity, you should start with log p, then you maximize it when, right, Alper? I'm just remarking what you have told me last time. Good. So we are good, right? Where were we? We were, I showed you that our theory was in accordance with our numerical calculation, if you remember. But we didn't talk about the code. We just saw this, right? So let me tell you what's going on in this code, if it's okay with you. First of all, what you need is collision, right? How do you define collision? Let me talk about elastic collision. Now, we are assuming that all these balls are equivalent and they have the same mass. So what we are wondering is, when one of them crashes into the other one, what happens next? So like if you start with v1 as a vector, and let's say v2 as a vector, doesn't need to be in the same direction, like could be like this, okay? It's a very general thing. So then maybe this one goes with v1 prime, and this one bounces like this, v2 prime. So how can I go from v1, v2 to v1 prime and v2 prime? That could be the question. And the way to do it is to first define a coordinate system. So we have some r1, r2, okay? And it's easier if you move, I will not show you the derivation, but you can do it yourself. It's easier if you move everything to center of mass reference frame, meaning that it's v1 plus v2 over 2. So in that center of mass reference frame, things become symmetric and whatnot. For example, one symmetricity is that v1 prime plus v2 prime over 2 will be the same. So center of mass velocity will be preserved. And once you do all the algebra, you get this one. v1 prime is v1 minus this whole thing, v1 minus v2 dot product r1 minus r2 over r1 minus r2 squared times r1 minus r2. And you can write similar things for v2 prime. So how is it implemented in the code? It's implemented over here. So I get an RP, the position of jth ball minus ith ball, and I take the norm of that vector as well. Okay. There is one thing that there is the when they collide, right? When do they collide? They have to be, first of all, the distances. The distance between them should be less than twice their radius, right? That's this if statement, And also, they should be actually in the state of collision. So maybe they are close by, but they have already collided and they are moving apart. So no need to collide them again. Because if you do that, it's just the same thing as having like a boundary. And do you remember, like you should be r away from the boundary, but you should also be moving in that direction, right? To not double collide stuff. Okay, and then this formula is what I have shown you. Dot product of RV and RP. So dot product of this one, the vectors, divided by the magnitude squared, and yeah. So am I missing? Okay. This is just some value, and then I add or subtract it from the velocities. I thought that I was missing a plus or minus here, but no, I just calculate this one and then I add it accordingly to the balls. Okay, so far so good. How about, so you will have multiple balls here, like 300 balls. If you go one by one over them, it's n squared operations. So what I did here is not that very complicated. So I made it faster by doing the least amount of work. So what I'm doing is I'm sorting their x positions. I'm sorting their x coordinates. So all the balls at each time step are sorted with respect to their, so the leftmost is called 0, and then 1, 2, 3, 4, 5. And then as I'm going over their indices, whenever their x positions are larger than 2 times the radius, I break the loop. So okay. These are the balls. And you can improve it much more. These are the balls. So I start from this one, 0. And then this one is 1. Maybe their x coordinate is less than 2r. So I still consider it. I look at its distance. And if it's larger, they are not colliding, right? But then once I hit here, which is already larger than the radius, I stop looking for this one, this one, this one, this one, this one as well. Do you see my point? You can do this also in the y coordinate, but then the program becomes complicated. Indeed, what was it called? there is something called quad tree. So you divide it into 4 regions, then you divide it into 4 regions again, 4 regions again. Like if you are a computer scientist, you are really into those kinds of divide and conquer kinds of algorithms. But this is a simple way of taking it. I believe it takes it from n squared down to n, or something like that. Do you have any questions here? Did you follow this? So that's how they collide. Let me tell you how I calculate the kinetic energy. Let me think. So here's what I'm doing here. I'm taking the mv squared over 2's for all particles, and I'm adding it to a list. I call that list EK hist. Okay. Later on, I will do a histogram out of it. That list grows as I run the calculation. That list grows, and whenever it hits larger than 1,000, whenever I have 1,001 such lists of energies, what do? I flatten it and make a histogram. So I have all these stacks of energies for each time step. I have 1,001 time steps. I flatten them together and make a histogram. Does it make sense? Yes?
What is flattening?
Flattening is when you have lists, for example, lists of lists, let's say. Maybe you have a matrix, 5 by 4 by 5 matrix. Then when you flatten it, it just writes the whole data as one line. Okay? So I don't care which one came first, which one came later. I just care about every 1,000 time step. I look at all the kinetic energies up to that point. Why I'm doing this? Because I'm trying to increase my statistics. I'm doing it with a few balls. By a few, I mean 200. Okay? But if you need, this whole thing is based on 10 to the 23 kind of thing. So as many statistics you have, the better your plots will look, right? With less ambiguity. So far, do you have any question? No question? Okay. How do I calculate temperature? Here I'm using a little bit of knowledge of thermodynamics, the macroscopic thermodynamics, okay? I'm cheating because everything else is really microscopic thermodynamics. You will see, like we will define pressure by microscopic thermodynamics, entropy, etc. But when it comes to temperature, I just think of this one. Normally in 3D, CV for 2D. Let's talk about this. So for 3D, in 3D, you have kinetic energy equals to 3 over 2 n kBT. Do you agree with this? From classical thermodynamics, ideal gas stuff. Now this is degrees of freedom. Degrees of freedom. So you have 3 dimensions, you have only translational symmetry, so you have 3 degrees of freedom. When you have 2 dimensions, you have 2 degrees of freedom. So in 2 dimensions, in 2D, kinetic energy is equal to 2 over 2 n kBT. So temperature is really kinetic energy over n kB. And we take kB to be 1 in this universe, okay? So that's why it's simply the kinetic energy, the sum of the kinetic energies, divided by the number of poles, okay? And it works only if you take into account this 2D thing. So what is CV in 2D? It's 1. What is CV in 3D? It's 3 over 2. Do you remember CV, CP stuff? Yeah. Vague memories of those things? Very good. So as I mentioned earlier, if you run this, do I need to specify anything else? Are you wondering how it works otherwise?
What is the 0.5 there? 0.5?
1/2 mv squared over 2. Sorry, it's mv squared over 2, right? It's the kinetic energy. So that 1/2 is 0.5. Happy?
Why is there a while loop? Because it says while true, I'm not seeing how it's becoming false or when you're breaking out of the loop.
How it becomes what?
How are we breaking out of this loop? When
Interrupt.
okay.
Yeah.
Otherwise it's
Yeah. It's a stupid code. Yes.
In the homework you can say 1 million there.
Yeah. I mean, you can write something there. Thank you.
Cambridge asked us to do it 10 million times.
Ooh, nice. So you are convinced with energy distribution, right? E to the power of minus E over kBt, and it fits. Now let's talk about speed distribution. So let's talk about speed distribution. Let's also say in 2D. So let me start with in 3D. You have this Vx, Vy, Vz, right? And you can think of it as a sphere and a certain value of velocity. So how many states, imagine you have like states here. How many states would you have in this, inside this? It would be proportional with v squared, right? Because the surface of the sphere is 4 pi v squared, right? So it would be proportional with v squared. That's the number of states that you would have. But you also multiply it with the Boltzmann coefficient, which is like mv squared over 2 kBt. So far, so good? This is Maxwell-Boltzmann distribution for 3 dimensions, right? Now let's go to 2 dimensions. In 2D, this time you have only Vx and Vy, and the number of states grow proportional to V. Again, you have this Maxwell-Boltzmann distribution, right? So that's what we are expecting to get in 2D. So far, so good. What do we mean by velocity distribution? We mean the same kind of a plot, but this time for velocity in this direction and probability of being at that velocity. So if you plot this, it looks like this for 2D. So let's see if we are getting it. Let me move over the code. So this time I'm getting the speed histogram, and what I'm doing is I'm just keeping the tab of all the velocities, right? Should I run this? Okay. While it's running, let's see what we are doing here. We are getting the histogram points here, and then we are getting the histograms, the values at the histogram, and we are saying that, okay, theoretically, it should be that histogram values, V times e to the minus v squared over 2 kBt. Yes? So it should fit. And it is fitting. How nice. Are you happy? Do you have any questions? Moving too fast? Too slow? It's okay. So that's how I stop things. Interrupt. What is the next subject? Entropy from phase space. I hope you have ate a good meal, had a good sleep, because okay. What is phase space? So in classical physics, the information about the system is fully present when you have the x values and v values of something. Like, for example, one particle, if you know the x value and v value, this whole thing, when you have x and v together, is called the phase space. And you have all the information. If it's here, let's say it's harmonic oscillator, this is telling you that it started from some stretching and it also had some positive velocity. So what will happen? It will stretch all the way, come back, and go like this. Okay? So if you know the points of particles in phase space, then you can predict its future. But what we are doing is, we know that the information is somewhere there in the phase space, but we are calculating how ignorant are we about that information. Does it make sense? Like, what we are going to do is this. We are going to parcel the phase space into some squares like this. And we are going to count how many particles are here, how many particles are there, how many particles are here, etc. How many particles have this position and this velocity? How many particles have this position and that velocity, etc. So that will be what we are going to calculate, and then we will turn it into a probability distribution. And then we are going to do minus pi ln pi. So all these are going to be your pi's. Like, how many particles, what's the probability of having a particle here? What's the probability of having a particle over there? P1, P2, etc. Does it make sense? Yeah. To everyone? Very good.
Only x coordinate. Where is the y coordinate?
Exactly. It's just hard to draw four dimensions because we six. We have two-dimensional system, so we need x coordinate, y coordinates, and vx and vy. Do you agree? So it's, as you said, it's really a four-dimensional space. Okay. Four-dimensional space, and we are going to parcel it, or should I call parse it? Parcel is something. Anyways. Okay, I'm waiting for the jokes to stop. They keep going. Good. So what we have done before? We looked at a state at a certain moment. We had some velocities. We put histograms. Now we are going to have something that we will call state, and we will sum over q states. We will gather the information in q states, and we will have x coordinate, y coordinate, vx coordinate, vy coordinate. Okay? So what we are going to do is we are going to discretize each dimension into m points. Okay? I take a system. I look at my particle's position, where it is in X. I mean, in one of the grid points, right? In one of the regions. Out of 10, where it is. Where it is in X, where it is in Y, where it is in Vx, where it is in Vy. And I just add one particle there. Then I keep doing it for all particles. Then I keep doing it for Q time steps. Make sense? Once I'm done, I sum over this Q so that I get only the X, Y, Vx, Vy. So I have M by M by M by M matrix. Okay. Then I flatten it, right? Flatten it, divide by its sum because it becomes, that's why it becomes probability. Then I do P log P. Let me show you. Let me show you. So I define some minimum X, which is Lx negative, minimum Y, Ly negative, maximum X, Lx positive, maximum Y, Ly positive. These are the box edges. It's easier for X, Y to define this. But how do I define V mean and V max? Well, I get it from this plot. I see that it goes between 0 and 5, and I presume that Vx's and Vy's don't exceed 5. Do you agree with that understanding? Hopefully you agree. Then I start with states. All of them are 0, Q by M by M by M by M. And M is 10 because it's M to the power of 4. If I make it 20, it's 16 times more calculations needed. Okay. I start the time. I start by empty entropy. And then the states at the qth time. Okay, what I am doing here, can you tell me? What is this percentage? Remainder? Mod? Isn't it mod? Do you call it remainder as well? Does matter. I see. Yeah, it's remainder as well, right? Anyways, why do I use it? Well, what I'm doing is, as the time progresses, I want to look at the last Q time steps. Okay? At the last Q time steps. So, as the time progresses, I look at this moment and the Q before that, all of them. So, the way to do it is that I put the data here, here, and once it's filled, I start erasing this data and putting the new data there. Does it make sense? Does it make sense? No?
Q is 100, so you put 100 of them and then you start again?
I don't erase what I put so far. I just change the 0th one, update the 0th one, and that way I keep the tab for the last 100 time steps. Because the order doesn't matter. The order doesn't matter. What matters is I have the data for the last 100 time steps. Okay? Well, what is this? What are these lines doing? I, J, K, L. Any ideas? Let me explain. So I have discretized every direction. So this is x min, this is x max. Okay. Let's say you have some x. Where does it fall? There are m possibilities. So what it does is x minus x min divided by x max minus x min times m and make an integer. That way it finds which slot it belongs to, right? The x position, y position, vx and vy. So I get the relevant slot for x, the relevant slot for y, for vx and vy. So far so good. Then I add one state there. So I have 100 by 10 by 10 by 10 by 10, a hotel that has like 100, I have 100 cities, 10 hotels in each city. Every hotel has 10 stories, etc. Each one has 10 corridors, and each corridor has 10 rooms. So I'm finding where to put my state. Okay, it's in the seventh city, la 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 la. Okay, I put it there. Then what do? I flatten it. Once I sum it over queues, I flatten it and I do this, make it a probability by dividing it by the sum. Then I sum over p times log p. And I avoid the zeros because 0 times log 0 is not 0 in Python, but it is 0 theoretically. So far so good. Do you have any questions? Okay. So I'm going to run the same program, the same balls hitting each other. Let's see how entropy changes. It starts from a lower value. It increases because we have started it from a special value, like we have started it from something that we arranged, not something that was natural, okay? But after some time, it settles into maximum entropy. I think I should, do you remember the flipping game? The flipping game would flip the things and it would naturally go to maximum entropy state. Why? Because those states are much more abundant than everything else. So even if you are doing a random walk, you are bumped into those states, the maximum entropy states, much more frequently than the minimum entropy states. Okay? If you don't clear your room, it will itself move towards disorder, towards, like, let's say all pencils are in the cup, right? That's a state. But that's a very limited state. Pencils could be everywhere, right? Those are much more, there are much more probabilities of pencils being everywhere. So, yeah. We can do all kinds of philosophy here. So how come pencils are there? How come when the very fundamental law of nature is increase in entropy, pencils get to be in one place? How do we have pencils at first place? Well, the answer is that every order that you create, you pay maybe hundreds of times price in terms of entropy. You create entropy to make that. How? Well, the plants get the energy from the sun, then the sheep eats. It takes a lot of time for them to grow. Then it takes a lot of time for the sheep to grow by grazing. Then you just cut it and eat it and do your business. So you are responsible for all those entropy increases just to make a pencil, right? But don't feel guilty. This is the way nature works. Okay. Do you see that our entropy calculation makes sense physically? as well. Okay, let's have some fun. What we are going to do is we are going to have a box, and then suddenly we will increase its size to 2 times. Okay. Are we doing it already? No. Okay, this is my box. This is my entropy. Okay. Do you see the entropy? Started from a low value, then it jumped up to a certain value, and it fluctuates there. So far you have just balls hitting to the wall. Then at certain point, I'm going to double the size in y direction. Okay? So far it's at equilibrium and it's just hanging out. Then suddenly it's double, and suddenly everyone starts rushing to the right, and entropy decreases, right, momentarily. Would you expect, if you increase the volume of a room, would you expect entropy to increase or decrease? Increase. Why?
Because there's more room to mess.
More room to miss out. And indeed, oh, did it stop? Okay. Wasn't supposed to stop. RAM bitmiş? No. Come on. Okay. Yeah. So you expect the entropy to increase, and eventually it increases. You see, our intuition for entropy is always based on equilibrium. We say that the entropy will increase because that's the maximum entropy for a larger room. But what happens in between? What happens when it's at a non-equilibrium state? Well, let's remember what entropy was. It was ignorance. But do you see that when it increases the size, at that particular moment, I actually do know, oh, it stopped. It's fine. I actually do know that there are before I didn't know whether particles go to the left or to the right. It was equal probability. But since I increased the size suddenly, I actually do know that there are much more particles going in the right direction. So momentarily, I'm creating less ignorance. Yes? Do you see? And it actually, it is possible to see it in the outcome. Are you convinced that the entropy decreases and then increases? Do you have any problem with that? Do you have any suggestions, like you did something wrong there, etc., or doesn't make sense? Does it make sense? Yes?
Why it decreases at the first?
Yeah. Because before it opens up, I don't know an extra information about the x direction velocity. The moment it opens up, I receive an extra information that significant portion of the particles will be moving to the right. So that's an extra information which decreases my ignorance. Okay? But momentarily. Once they start hitting the other wall, it mixes up again, and this time entropy increases to the point where it was even before, larger than before, because now, as Alper said, I have more room to mess up the system. So more room, more entropy, but momentarily it decreases. I think it was enough to give you a sense of non-equilibrium thermodynamics. Okay? Oh, it was a long code. Maybe that's why it was crashing. So do I need to explain any code here? Not really, right? You understand what's going on. It's just this part is different. No, this is another code. This is isothermal adiabatic expansion. I'm talking about this one. Do you see? When t is greater than 1,000, after 1,000 steps, suddenly LXP goes from 200 to 600. So,
I have an idea.
yes.
What about doing this for t greater than 100 instead? So it's already very close to equilibrium, so it will expand earlier and we will get to see it reach the equilibrium.
Okay.
Before it's crashed.
Exactly. So, let's try it.
And what about compressing? Did you try it?
Yeah. It will be. Did it start or did it? Where am I? Sudden expansion. So did I change it correctly? Okay. Do I need to restart again? So I get the decrease. Okay. I actually do know what's going on. Okay. Where is it? Okay.
No, isothermal solution.
Okay. Yeah. It's coming out of this one because, okay, it will be fixed hopefully if I increase this to 6, maybe. Let's see. I think the problem was that some of the particles got faster than 6, and when it gets faster than 6, it doesn't know. I mean, the hotel doesn't have enough rooms anymore. Are you convinced now? Yes? Do you like it, Alper?
Yeah.
Very nice. Hopefully you are with me still. Do you need a break? Yes.
We can ask you a question.
Sure.
We know that the entropy jiggles around the equilibrium.
Yes.
But how do we quantify how much it jiggles?
Let me answer that during the break. Okay.